Hey everyone, let's dive into this pile of papers about parallel processing. Making computers faster. It seems like adding more processors should do the trick, right?
Yeah, you'd think so.
But these papers you send over, they get into Amdahl's law, Gustafson's law. There's some counterintuitive stuff in there about multi-core chips and all that.
It's really interesting how relevant those ideas from decades ago are today, with multi-core processors everywhere.
Let's rewind the clock a bit, like back to 1967.
Groovy.
Right. So picture this. Gene Amdahl, already a big name in computing, presents this paper
At a conference, yeah.
and kind of shakes things up. Everyone's excited about parallel processing, like having multiple cooks in the kitchen to get that dinner ready faster.
Many hands make light work, or so they thought.
Oh.
Amdahl's law basically said, not so fast. There's a catch.
Yeah, what was the catch?
Well, imagine those cooks, right? They can chop veggies and mix batter at the same time. But someone still has to bake the cake. That part, the sequential part, that doesn't magically speed up just because you have more people.
So even with a ton of processors, there are parts of a program that just have to go step by step.
Exactly, and that's what Amdahl's law is all about. Is the part of the program that can't be broken down into parallel tasks. That's what limits the overall speedup. You could have infinite processors, but if 10% of the program has to run sequentially.
You're stuck with, at best, a 10x speed increase.
Exactly. And what's funny is, back in '67, Amdahl wasn't even thinking about the multi-core chips we have now, with hundreds of processors.
He was thinking even bigger.
He was actually arguing that a single powerful processor could still outperform a bunch of slower ones.
Wow. So even back
He
then,
was ahead of his time.
the seeds of this debate were there. Fascinating stuff.
Yeah, but he makes a good point,
You're right.
about focusing on what the processor's actually good at.
Totally. Like those AI chips you were talking about, that's Amdahl's law in action. Okay, but this is just part of the story, right? We have to talk about Gustafson's law now.
Absolutely. Gustafson comes along a couple decades later.
At Sandia Labs, right.
Yeah, Sandia. They were doing some pretty massive computations. He kind of said, okay, Amdahl's law is true, but
But,
it doesn't tell the whole story. See, Amdahl was talking about a fixed problem, right?
yeah,
Like, how do you make the same task faster?
by throwing more processors at it.
Right.
Yeah.
But Gustafson said, well, as our computers get more powerful,
We get more ambitious with what we want them to do.
exactly. We don't just keep solving the same problems, we try bigger ones.
Okay, so instead of 10 cooks making one cake faster,
You give them a huge EE kitchen, tons of ovens.
and they make hundreds of cakes.
There you go. That's Gustafson's law. More power means we do more stuff, not just the same stuff faster.
And he had the data to back it up, right? From those huge parallel systems at Sandia.
Oh, yeah. They were getting near linear speedups, even with thousands of processors, which Amdahl might have said was impossible.
So what does this mean for our listeners? For people who aren't designing supercomputers but still deal with big data, complex problems?
It's really about thinking differently, not just about raw power.
Right. It's about using that power the right way. Which brings us to multi-core processors. We've got Amdahl, we've got Gustafson. Now we have to actually build the chips. How do we design them to make the most of parallel processing?
That's the question, isn't it? It's a whole different world for chip designers. Instead of just one processor, faster and faster, now it's about finding that balance, sequential and parallel, right there on the chip.
And we've got all these different models. I was reading about symmetric, asymmetric, even dynamic multi-core designs. What's the difference?
Well, let's start with symmetric. That's the simplest, really.
Yeah.
All the cores on the chip, they're identical.
A well-drilled team, everyone has the same skills.
Exactly. But of course, you can only make each core so powerful if you're fitting a bunch of them on one chip.
Right, there's got to be a trade-off somewhere.
And that's where asymmetric comes in. This is where it gets cool. Instead of all cores being the same, you have a few really powerful ones.
For those sequential tasks. Amdahl's law, right there.
Yep. And then you surround those with a bunch of smaller cores that are great at parallel stuff,
So it's like having a lead engineer for the complex stuff.
with a team of specialists to help them out. And that can be really effective for a lot of tasks.
Yeah.
But the holy grail,
Yeah.
that's the dynamic model.
Dynamic, what's that? Like cores that can change on the fly.
Exactly. They could combine to be super powerful for sequential stuff or split up for parallel.
Yeah.
Adapt to whatever you're doing.
Wow. That sounds incredibly complicated to design.
Oh, it is. And that paper you sent, it made a good point about the cost, this kind of dynamic design. Maybe for a supercomputer, but for your average phone.
Yeah.
So a whole other challenge.
So to wrap this all up, we've covered a lot. Amdahl's law, Gustafson's law, different ways to design chips. What's the one thing our listeners should take away from all this?
I think it's about understanding that more cores, faster clock speeds, those aren't the only things that matter. You have to know the problem you're trying to solve. Can it be parallelized? How much of it is sequential? Amdahl and Gustafson, they give us a framework for thinking about that.
It's about working smarter, not just harder. And that might mean better algorithms, the right software, even changing the problem itself to make it easier to parallelize.
Totally. Hardware is just one piece of the puzzle.
It really makes you think. If we keep making computers more powerful and our ambitions grow to match, where does it end? Do we hit a wall? Does Amdahl have the last laugh? Or do we find entirely new ways to think about computing? Something to ponder. And on that note, thanks for joining us for this deep dive into the fascinating world of parallel processing.